Hello, friends. So, welcome back to Material Science and Metallurgy course. And myself, Dr. Devarun, Associate Professor and Head of the Department of Mechanical Engineering at BB Raj Institute of Technology in Narsapur. So, as I was discussing about the different crystal structures, important terminology, and a few definitions on how the lattice structures are formed and all. So, we'll continue and we'll discuss about the crystal structure in detail in this session. Yeah. So here in the unit cell, let us first understand the unit cell. So unit cell is basically nothing but when you have the entire crystal structure in the three-dimensional space, the smallest entity that represents the entire three-dimensional, like in case of Lego, which I showed you. So the small Lego is the building block and it represents the entire building. So if you want to understand the entire building, you start with that building block. In the same way, we are going to examine in the entire crystal structure, which is in three dimension, this smallest unit cell, and we will try to understand it in terms of side and angle and also how they are positioned. So in order to go to that extent, first you need to understand how are these unit cell represented. So in the entire three-dimensional space, what is called as a unit cell or how do you represent the unit cell? So first we will see if we consider one dimension, that is atom star arranged in a row or in a column or in only in one dimension. So let's say these atoms, these yellow spheres are arranged in one array like it is shown in this case. So what is the smallest division that we can make? So let's say this blue portion which is marked, can we call this as a unit cell? Or there is a possibility of considering it between two atoms so that the space is also covered. So this red portion. Or I can take from one end to this end, considering like three or four or something like that. So green one. Obviously, this is the bigger possibility, and this is not the smallest one. So obviously, this is cannot be called as a unit cell. Then between these two, which one is better representation? So if I take the blue portion, it is not considering the distance between the two atom, whereas here if you see, this is able to even capture the distance between. So compared to the entire atom inscribed in a cube, it is better to have even the distance like the part of it. But it has to be perfect. Why? The reason being this has to be repetitive. So if I show this part and then repeat it, it is possible in this case. So anything that is repeating segment, that crystal is the basis one. So this one, let us move it for representing it with with the gap between the two atoms. So, like we have already seen, if they are touching each other, which generally they don't, if they are touching each other, this is how it will be represented. And we have understood very clearly that blue one is not a correct representation because if there is any gap, this and this both are not valid representation. So, blue one is not possible. Let us consider this red one where we take half portion of the unit cell and we'll also consider the gap between them, and let's go for the next one. So if there is any gap, this is a valid representation. So you can see very clearly this is able to capture even the gap. So this red representation is valid. Remember, this is only the case study where I am just trying to show you for two dimension. Now we'll come to a very important one, which is all which makes sense for all the representations. That is about the atomic packing factor. In short, APF. So when we take about any unit cell, the unit cell may have certain volume and we need to calculate how much is the volume of these atoms occupied in that particular unit cell. So it is represented by this notation by a formula given atomic packing factor is equal to volume of atoms in a unit cell divided by total volume of that unit cell. Very simple. Suppose you have that cube which is filled by certain atoms. We are asking you to find out what is the volume occupied by these atoms in the entire volume of that cube. So that represents the atomic packing factor. Now, with this information, we will be able to understand what is the volume of atoms in that particular unit cell, meaning how much is occupied and how much is empty or void spaces, with which we'll be able to, in future, we'll be able to correlate and understand how much is vacant, how much can be fitted, in the sense if atoms has to be alloyed, there is either a substitutional type or interstitial type, which we'll be learning in the next few sessions. So, where is the possibility? How much is can be added into this unit cell? So that meaning we can extract, or that inference we can get with the value of atomic packing factor. So this is generally measured in terms of volume of atoms in a unit cell divided by total volume into 100 to give it in a percentage wise. So, okay, so let's see how we can determine the atomic packing factor when the atoms are arranged in a one row. So let us consider with one dimensional again. So if suppose we take these four atoms touching each other as one particular unit cell, and we could take here as the unit cell. So if at all I want this length, it is straight away 1 r, 2 r, and again 2 r, and half 1 r. So this total length will become 6 r. And 6 r divided by again 6 r, it will be 100%. But when we arrange them in the two-dimensional, then we may encounter this type of arrangement of atoms. And in this one, like we can clearly know this length, which is in the diagonal, because they are touching each other. So I can take this as R, 2r, and one more R, 4r. And if I want this side, that is again, like we know the Pythagoras theorem, so it will can be easily calculated as 2 root 2 r. So for this one, if at all I want the unit cell atomic packing factor, then it will be the r in terms of a, that is side, which is 2 root 2 r, right? So it is nothing but the length of the circle in the red line, that is this red line, is 4r. And the length of this red line is 2 times of 2 root 2r, which is nothing but atomic packing factor is root 2 by 2, which is 74.07%. Anyway, all this is mainly done to make you understand how we are trying to calculate the atomic packing factor for three-dimensional. So these things are generally to make you understand when they are arranged in two-dimensional or in one dimension. So moving forward, if suppose the same thing, if they are arranged in the atoms are arranged in this systematic manner, you will get atomic packing factor as 78.54. And if it is in this type of arrangement, it is 78.54 again. Like the calculation goes on. You can go through. Let me go to very important type of crystal structure, which is simple basic crystal structure, simple cubic crystal structure. So in the simple cubic crystal structure, like you can see, these arrangement is in along the vertices, and when they are in along the vertices, and we know that it is a cube, so a equal to b equal to c, and obviously alpha equal to beta equal to gamma equal to 90 degrees. Now, if you observe closely, since atoms are touching along their edges, so we can take that as this is half times 2r, half times 2r. So it is 2r straight away. So the relationship between A and R is A is equal to 2 times R. This is for simple cubic. It may vary for different things. This is the first thing that you need to know about A in terms of R. Next, and the simple cubic as 52 percentage. Now, moving on, there is another important one, which is body centered. When you have this, see here and imagine like they are touching along the diagonal. So, if you see this diagonal, they have R, 2R, and R. So, which is 4R, the green line. So, green line we know. We want to know the side, which is this blue one, isn't it? So we know green line, we want the blue line, and the red one is also not known to us. So we can calculate this red one because even this is the diagonal face, and the other two sides are A. So we can first bring that relationship. That is, so if you take this as D and these two are A, because this is cubed, so both the sides will be equal. So then it will be 2A. So 2A square, by Pythagoras theorem, 2A square is equal to D square. So we can replace this D with 2A square. So now the new relationship here is A square plus 2A square is equal to 4R square. Okay. So once we make the entire simplification, the A will be equal to 4 by root 3 R. Now here we got for body centered, A is equal to 4 by root 3 R. Earlier, if you remember, we had A is equal to 2 root 2 R. And here we got A is equal to 4 by 3 R. We had body centered as 68 percentage. Now, by knowing this information, again, we need to calculate what is the volume of the atoms, which is nothing but 8 into 1 by 8 corner portion. Plus, if you see closely, there are six sides. On six sides, you have half of an atom. So 6 into 1 by 2. So 8 into 1 by 8 plus 6 into 1 by 2. 8 into a 1 by 8 will give 1. 6 into 1 by 2 will give 3. So 3 plus 1, 4. And volume of the sphere is 4 by 3 pi r cube. So 4 into 4 by 3 pi r cube. And again, the denominator volume of the unit cell remains the same, which is a is a cube, which is nothing but 2 root 2 r, which is once you simplify, you will get pi by 3 root 2, which is nothing but 74 percentage. So far, you got this as 74 percentage compared to the previous, if you remember. Okay. So let's quickly see the last one, which is hexagonal closely packed (HCP). In the HCP, as you see, A is equal to B, but B is not equal to C, and you have to have a complex relationship with one is A in terms of R, and again C is in terms of R, and then we need to have C and A as a relationship, and finally what we have here is C is equal to 4 root 2 by 3 R. And once we know this relationship, we can calculate the volume of a unit cell. As you can see, you have 12 atoms which are on the top and at the bottom, and they are taking 1/6 portion. And you can see there are three full atoms at the middle, and on the faces on the top and on the side bottom you have half. So summing up, we have 6 into 4 by 3 pi r cube, and in the previous what we discussed, we have the relationship which will give us the denominator volume of a unit cell, and once you simplify you get pi by 3 root 2, which is again 74 percentage. So these are the basic important crystal structures. So we have discussed simple cubic, face-centered cubic structure, basics, uh, and also hexagonal closely packed. So with this, I'll stop here, and I hope you have enjoyed. And see you next time.